Alright, looks like we're on. Okay. So the last thing in our notes would be the plane polar coordinates, right? So we're gonna start with those again. Make our way through a couple of examples. Plane polar coordinates. Okay. So I'll just start once again with the general definition. You're here in the XY plane. You have a point in space, and you characterize it by the distance from the origin and the angle with respect to the positive x-axis. And then you can write for your two-dimensional vector, r hat, where this r hat is just unit vector cos theta sine theta. Yeah, and I'll put the r hat right here, unit vector. And then you differentiate, and you can get derivative here is r dot r hat plus r phi dot phi hat. And this time we have a unit vector which just comes from the derivative of this minus sine theta cos theta. And if we sketch it up here, it's a unit vector and it's perpendicular to r hat. Then you can form r dot squared, which is v squared, and then your unit vector and perpendicular nature of these things comes in handy, and we find r dot squared, r squared, v dot squared, and v squared is going to turn out to be a very important quantity farther down in physics. Already is, but we'll see more of it. And then finally, I did the second derivative, and I end up with two components of the acceleration. So this is the r hat direction, and the phi hat direction is 2 r dot phi dot plus the second derivative of the phi hat direction. So anyway, this decomposition looks complicated at first. However, it has some really nice features. And we already saw that if you have constant bar, you get your circular motion formalism back. And I'm going to do another example. And then under this, we had this in our notes last time too. I'll add that to the mix. So for Newton's law, we will then have m r double dot minus r v dot squared equals, I'll say f sub r. So that's mass times acceleration in the r hat direction, force projected on the r hat direction, and then mass times 2 r dot v dot plus r v double dot. Going to be f onto the phi hat direction. So that's Newton's law. And the example we're going to do now, we did one last time. Our next example, let's see if we've got room for it. It's going to be the simple pendulum. Okay. The simple pendulum is a good one. And we can do a couple things with it. So I'll just hang the simple pendulum from here. It's restricted to motion along that arc there. So I'll have my angle phi like so. And we're going to be in a vertical gravitational field, right, for a pendulum. So what we want to do is write down these two Newton's laws. And what I'll do is I'll put the force. Yeah, this picture I could have made a little bigger, but you guys can do it anyway. So we've got the weight acting in the down direction. We're going to have a tension. I'll use capital T. We'll have a tension along the string. And that actually should suffice, but I'm still going to indicate my R hat and my phi hat vectors that are perpendicular to each other. So yeah, now let's look at Newton's law here, one step at a time. So here, R equals L is constant. Okay, so we got a constant length string. Of course, we've got our mass right there. So what does Newton's law turn into? Here we're going to have minus m L E squared equals the force along the radial direction. But we have two forces along the radial direction. So what are those two forces along the radial direction? Anybody? All right, we're doing Newton's law. I've just evaluated this. This was a 0, negative mr phi dot squared. It's the left side. The right side, I need the force along this radial direction here. So we've got a tension. And
there is a component of mg.
of mg, right? And interestingly, we're going to put a minus sign in front of the tension because we're doing it along the direction of the r hat vector. Would be so the positive direction is out. So we've got a minus t, and then we've got plus mg cos phi. So there's Newton's law. I'm going to turn that into a homework problem in a minute, but for the moment, there it is. And the second equation, this one we'll go ahead and continue on ourselves here in class. So again, we're looking at this equation. We have r dot is 0, so we have m, and r is equal to L. So we have m r phi second derivative. No, sorry, L. Make up your mind, right? M L phi double dot. And what is the force component along the phi hat direction? I can put hats on these, but I'm not going to. Along the phi hat direction.
Mg sign.
It's going to be mg sine, but it's opposite the phi hat direction. So it's minus mg sine of phi. Good. For this one, we can now do a small angle approximation. Now, when phi is much less than 1 in radians, we get phi second derivative minus g over L times phi. Okay. We can just declare the nature of that differential equation and its solution just right off the bat. We were talking about that last time. You should just be able to look at this and then write what happens then.
Harmonic oscillator.
Yeah, it's going to be a harmonic oscillator. What's the frequency?
Constant. G over L.
Square root. Right. Exactly. So omega equals root G over L. Phi of t you have that, and this is a second order differential equation with constant coefficients minus sine going down. Does anybody remember the period of the pendulum? I'll just sneak that in right here as an added note. Omega t equals 2 pi, so the period, generally speaking, 2 pi over omega, 2 pi root L over G. So that's that famous property of the simple pendulum that the period goes with the square root of the length. And this is a useful formula to have. You can always have a clock on hand. You just take a pebble and a piece of string and time whatever.
So show it like for small angles.
Small angles only, yeah. And you know, we did that here. It's only true for small angles. We're going to investigate that later. There is a amplitude dependence of the period for the pendulum, but the amplitude dependence of the period, like if you did period of amplitude and you were to graph that, it'll have a local minimum call that phi naught right there, initial amplitude. It'll have a local minimum and go up quadratically, which takes a bit of doing actually to find that property of the oscillator. But yeah, when you did the small angle approximation, so yeah, that's an important note here, small angle approximation. Angle approximation. Okay, so we took care of this one here. We've got ourselves a simple pendulum. There's an interesting thing we could get from this equation, namely we could find the tension in the string. Okay. And we weren't asking for the tension in the string, but now we are. What's the tension in the string? And you see it varies with the angle and the speed. So I'll turn this into an interesting little homework problem. Get some erase over here. So homework. Find tension T. And since we're talking about this concrete example of this pendulum right here, we want to solve for the tension T. When the initial angle phi sub naught is given. So tension as a function of the initial angle. You're not ready. This will actually be quick, so since it's halfway on the board already, what you see is we have mg cos phi minus plus ml phi dot squared. P is a function of phi. If phi naught equals pi over 2, what is T at the bottom? Right, that phi equals 0. So when the pendulum swings through the minimum, that's going to be your maximum tension. That's an interesting one. What you'll find out is it's 3 times the weight. So practical knowledge for rope swings and things. Tension can be considerably larger than just the weight of something is swinging through. And this is if you release it from rest. So we're releasing it from rest. And you're going to have to use, to solve it, you just have to use energy conservation. Which we have here, no friction. Use energy conservation to get that. It's an interesting problem. Okay. So those are some applications of plane polar coordinates. And we're gonna go up a notch by talking about spherical polar coordinates as well. What we're going to find though, well, what I'm going to point out is that when we do spherical polar coordinates, it gets a lot more complicated, but we don't actually have to go to the acceleration. So we'll just go through the velocity. Yeah, more about that later. So, is this clearly stated enough? I want to find the tension when initial angle is given, right? And then, so for this one here, phi naught is pi over 2, v naught equals 0. So we're releasing it from rest, just to make sure that's in your notes. So we're releasing the thing from rest, we'll hold it up here, release it from rest, and swing it back to what the tension is in the string. That's pretty basic. Okay. And actually, these examples give us one good application of these coordinates. When you're on a circle, you know, this is the simplest coordinate system. If you have motion on a circle. So X and Y would be more complicated. So the same thing goes for a sphere. If you have something restricted to a sphere, then your simplest coordinate system will be the spherical polars. Have about it.
Quick question.
Yeah.
You mentioned that like at the bottom, the extension would be 3 times as much as the
It'll actually be 3
weight.
times the weight, yeah.
Yeah. So if we have like a uniform circular motion in a gravitational field, like a pendulum, but it goes like all the way around.
Right.
So the centripetal acceleration at the bottom would be the strongest.
Yeah,
Okay.
that's right. And if you're whirling it around, you could have much more than 3 times the tension. That's if you released it from rest. So yeah. So our pendulum, we decided to release it from rest right here. And we're gonna find, that's just a good metaphor. We're gonna find that when it comes down here, it's gonna have 3 times, the string's gonna have 3 times potentially 3 times the weight, okay? So yeah, if you could release it from up here or give it a push, it could have much more tension. So if you're building roller coasters, you have to know this kind of thing. In fact, you have to know the acceleration at the bottom of the roller coaster. You can easily make people unconscious if you make the turns too tight, right? And say fighter pilots are people also, right? They're going through curves where the G forces are far more than E3. I think 3 is still okay, but if it's too high, they have to have suits that keep the blood up in their head, and then you can black out easily. So yeah, what a machine can do, is beyond what we can handle. Okay. So spherical polar coordinates. Only the mathematicians and the physicists label them a bit differently, so I'm going to use the physicists. Convention. So spherical polar coordinates, what you do is, look at it this way, make this adequately large. So now I have my X, Y, Z coordinates like that, okay? The perpendicular. And I have some point here. So I'd get a vector pointing to that point. And to characterize it, I'll project this onto the XY plane and call this angle phi. And then the projection onto the Z-axis, I'll call theta. And now I need my X, Y, and Z in terms of R, theta, and phi. So R, phi, theta. So the X component is going to be, and so again, the magnitude there is R length. X component is going to be R sine theta cos phi. So R sine theta gives me the length of the projection onto the XY plane, and then cos phi is the projection onto the x-axis. And then the y is going to be R start getting x dot, y dot, z dot, we just have to do a lot of chain rule. And we're actually going to do it both ways. We're going to do what we did with an r and an r hat. Or r equals r hat. And the r hat is what's left when I factor the r up there. So I have sine theta cos phi, sine theta sine phi cos theta. And that's my unit vector. And if you want to prove that that's a unit vector, by the way, you're going to square them and add them up, right? When you square this one, you get a sine squared theta. And here you also get a sine squared theta. So when you square these two, the first two, and add them up, you get sine squared theta times cosine squared phi plus sine squared phi. So that turns just into sine squared theta, then it's plus cosine squared theta, gives you a 1. So that kind of thing comes up a lot in this. Okay. So good, those are our our spherical polar coordinates. Let's see how much of this we want to do together. I'll put that as a note since I just stated that. Note we have r hat squared would be sine squared theta cosine squared phi. Sine squared theta sine squared phi plus cosine squared theta. And then these two here, I'm going to add up the sine squared theta plus cosine squared theta. Okay, so we've got that there. What about next we want to do r dot. We can do this r dot r hat plus r hat dot. So we have to find out what r hat dot is. And let's see if we can do that. R hat again was sine theta cos phi. Cos theta. So we're going to have a bit of product rule, chain rule. So we're taking the time derivative here. We have cos theta, theta dot cos phi plus sine theta negative sine phi dot. And we have cos theta theta dot sine phi plus sine theta cos phi dot. And we have minus sine theta. So we have to extract two unit vectors out of here. And there's going to be one with the theta dot and one with the phi dot. So let's see what we can do here. We're going to have theta dot cos theta cos phi room here. So minus theta. There we go. And in fact, this one we can pull out a sine theta. So sine theta p dot minus sine p cos p 0. And in fact, here we recognize one of our previous unit vectors. Okay. And here we would have here we would not change. So this is plus p dot sine theta phi hat, and this is theta dot theta hat. Now this one is trivially a unit vector. What about this one here? Square it, we get cosine squared plus sine squared is 1, sine squared, right? So they're both unit vectors. You know, I could assign as a homework problem to show their orthogonality now. So we have 3 unit vectors. I'm gonna have to write something here. We have 3 unit vectors. And I'm gonna actually have to do another picture of these just to show us what we found here. Now that I think about it, the same picture will be fine. Okay, so we're out here. There's our angle theta. There's our angle phi. So these 3 unit vectors that we found, we have r hat, just as before. The theta hat now, imagine sweeping theta down like this, then you can see your theta hat is going to be here, and your phi hat is going to be kind of hard to draw. Yeah, phi hat's that to draw. Maybe you can find a better drawing of that. But the phi hat is, imagine swinging, increasing phi, and the phi hat is going into the board. So from these 3 unit vectors, we have a right-hand system. So r hat, theta hat, phi hat, unit vectors. I just showed that. Are they mutually orthogonal? So the second property, mutually orthogonal. Might put that on homework, but that goes pretty fast again. But the third property is interesting. They form a right-hand system. So it's similar to what we had the other day. When we have these unit vectors, they seem to be trouble because they're all over the place, right? Very complicated, but they're unit vectors and they are orthogonal. They form a right-hand system. That's all we need to know. Okay. Right-hand system. And yeah, so let's write these things down. Just list them. By themselves here. So sine theta cos phi, sine theta sine phi cos theta now really after is to get our R dot squared. And by the way, how do you prove they're a right-hand system? Anybody? Take a vector products. Take a bunch of vector products. So the dot products prove they're mutually orthogonal. That goes fast. And then vector products will show you that they're right-hand system. So you have to see what you're looking at here. What you're going to get is R hat cross theta hat is equal to phi hat, and then theta hat cross phi hat is equal to R hat, and then phi hat cross theta R hat is equal to theta hat. That's what we're looking for. So you can see this didn't look that great, and if we were to do the second derivative, it could be even worse. Okay? But instead, we're just going to cut to the chase with our b squared, because all we need is b squared in this set of things. Let's see, should we have? Yeah. So anyway, so far so good. Let's just call this homework. So we want to make sure we do that. So now I can free up some of this side of the board here. Okay, I'm going to free this up. So we wanted to get this thing, and we needed this R hat dot. Man, I shouldn't have erased that. We just had that up there. What do we just have for R hat dot? Theta hat plus phi dot sine theta phi hat. Okay, okay, good. So what we'll do is we'll put this in here. So now velocity is equal to R dot R hat plus R theta dot, we have R theta dot theta hat plus R sine theta phi dot phi hat. So now that's the velocity vector, and the velocity squared, v squared, dotted into itself. Anybody can just read it off now. If these are orthogonal vectors, if you dot that in, well, we can't just read it off, but let's just go ahead and write it out and then read it off. Okay. So we're dotting these into themselves. R hat plus R theta dot theta hat plus R sine theta phi dot phi hat. Product with itself. Of course, we don't want to write out all 9 of these. Theta hat plus R sine theta phi dot phi hat. Okay, 3 times 3 would be 9. We don't have to do that. Why not? Because these vectors, being unit vectors and being mutually orthogonal, all mixed terms like R hat, theta hat, 0. So you're really just doing a sum of squares. So all those cross terms vanish. That's nice. And that's why these properties are so important. So what do we get for v squared? We just get r dot squared plus r squared theta dot squared plus r squared sine squared theta Yeah, who wants to do the acceleration on these? Okay. Ask for a rainy day, okay? But the reason we don't have to is when we start using these, we're going to use the Lagrangian method, and that automatically generates the correct differential equations. We'll do that next semester, actually. So if we're gonna do dynamics with these next semester, we'll use Lagrange's method. Saves you a lot of work. And you know, when coordinate systems start to get complicated, you really want a method that just delivers the proper equations without too much trouble. But yeah, if you just need the kinetic energy, here it is. Times 1/2 m, you got 1/2 mv squared. Okay, good. So that generalizes. Got that, so. Yeah, we haven't drawn a line under them yet. What do we have for this week so far? We have, there's 2 problems from last week. And a couple off this board. That's not bad. So yeah, these are all good for this Friday. I'll add a couple more. But you know, we may as well try to say, look at the pendulum with these, the so-called spherical pendulum. So the example we're going to do here, actually, we'll just start with motion that's restricted to a spherical surface. A spherical surface. And in that case, you know, you've got your R as constant, surface R equals capital R, right? And then, for example, your V squared, this one is now gone. You've got R squared theta dot squared plus R squared sine squared theta V dot squared. So now you have 2 dynamical variables instead of 1. One, and then so-called spherical pendulum. So now with the spherical pendulum, we're going to just suspend it from here. And we can measure our theta from the point, it makes most sense to measure theta from the point that hangs vertically down. And now you have motion in theta like a normal pendulum would be, like a planar pendulum, but you could also have phi as it circles around in that direction there. But you would still put your mg right here. I'll just put here with energy conservation. And again, you would have mg, you'd have attention, and the energy conservation. So let me see the Z. Okay, so So I've chosen the positive Z to be in that direction, right? So I would have to have E would be 1/2 mv squared plus, I'm gonna do this, negative mgz, right? Calling this the positive Z direction. Okay, good. We're gonna leave that right there for the moment. A few minutes, but we're gonna start, at least discussion wise, talking about central force. So, because that's what we're gonna need the plane polar coordinates for. And in the spherical polars as well. Okay, good, so we got that. Next major topic is the central force problem. And, you know, by extension, we'll talk about Newton gravity, Kepler's laws. Does anybody remember Newton's law of gravity?
Is that the big mass, small mass, gravity constant over radius squared, something,
Yes,
something?
separation distance squared, that's right. So that's the, that's the big application. And I was just wondering, there's a nice way to show how Newton derived it. But for that one has to also have Kepler's laws. Do you remember Kepler's laws of planetary motion?
Never learned them.
Never learned them. So we'll do them in a different, you remember them?
Equal areas and equal time.
Equal areas, equal times was one of them. Elliptical orbits is another one. And the third one is the law of periods. That was the best way to approach this, especially in 5 minutes. We'll just do the definition of the central force first. Good. Anyway, so, but yeah, we're gonna tie all these things together. This is really a center of the entire semester, in a sense, right? Getting to do Kepler's laws rigorously this time. So anyway, if you're doing a central force, we're back to this discussion. Remember we said we have, for a single point, we're always looking at this really general form, right? And in this case, so this is not central force, this is just general Newton's law for one point mass, okay? The central force is if you have a center of attraction or repulsion and some force acting towards that center. So formally, we'll end the hour with this. You're looking at a force that just depends on the distance here and the direction is just the unit vector pointing away from that force. That's the central force. So you can even see how what we were doing with the plane polar coordinates and the spherical polars is just designed to use this through central force, because this is your R hat that we've been talking about this whole time, right? And so equals some function of that displacement times R hat. So that defines the central force. If the force is towards a center of attraction or repulsion. And that's what we're gonna work with, but you see we had to have the plane polars for this because we had to have this R hat type of idea. Planes or the spherical polars. Good, let's leave it at that. And then we'll review this at some point, bring it all into focus. But for the moment, that's where we're headed. Central force. Major application. Good.